Let me start the recording and I'm gonna just say this clearly for the recording. If you come to class raw dogging it, no reading, just hitting it wild, just like woo, you will do worse. The point of the reading is to do it beforehand. Because every time you're exposed to material, whether it's in this class or another class, you understand it just a little bit better. If you never read it on your own, the first time you see it in class, you'll be lost. The second time after class, when you read it to yourself, you get it a little bit better. Think about how you could sandwich that. Yes, you don't really get it the first time you read it. And then you go to class and, oh, that's what the fuck was saying. And then you read it again by yourself, and now you're getting mastery. Now I know Gen Z, everyone here, Gen Z? Millennial? Okay. Y'all hate reading, right? You think the book sucks? Okay. Gotta read. It's the only thing that computers can't do as well as you. You can absorb stuff, turn it into your own memories, turn it into your own knowledge and experience. You want to be irreplaceable? You want a job? You want a career that's independent? Be someone who has knowledge up here. If you can only use Google, you are not better than a computer, right? Okay. That's the tirade of the day. And it's recorded. So I stand by almost all those words. So anyone want to do faster methods? Because we don't have a lot of time left, right? We got shit, where'd it go? We got faster methods today, initial value problems. And yeah, so I'm not gonna bump you up because you're ready to go on Monday. Then we can potentially have a catch up and debugging, but I kind of would like to just add a little bit more content here. Maybe we can put random numbers here when David arrives and we can talk to him. Then we have this thing called spring break. Woo! And that's when we're actually going to work the hardest, right? Catch up on everything that we've been fucking around on while we eat pizza for 2 days. Just kidding. It's a lot of pizza. I love me some pizza. Don't get me wrong. But I'm also going to be doing work because that's all the research that I just haven't fucking done. So then we come back, we do simultaneous equations. But at this point here, before we leave, you should have a proposal. Something really fleshed out. Not like, oh, I like the idea of sound. Like, I'm going to use this differential equation. We're going to solve it in 2 dimensions. Here's what I think the code will end up looking like. Not creating code, but having that plan, having that map, right? The thing that I asked you to keep drawing. It's almost like the class builds on the skills, right? Okay. And where are we headed? We're headed towards a final presentation. So keep that in the back of your mind. You don't know how to communicate the ideas that you're saying, you're going to feel not as confident, right? You want to practice your speaking skills. You want to practice the ability for you to talk about complex things. You practice in class, right? By reading ahead of time, understanding it for yourself, and maybe understanding that you don't get certain parts, right? That's a skill too. Being like, I think I understand this. This thing is still giving me trouble. I don't quite get it. And it's easy to just say that about that second part. I don't get anything. But there are lots of things that you do understand well. You just haven't built the confidence towards. So that's why talking about them helps. Okay, then we do chapter 5 and we're basically done. I mean, this is like 1, 2, 3, 4, 5, 5 weeks. The fuck? That's a month. And then I'm free to go to summer and go to as many baseball games as I want to. Okay. Any comments, questions? Since this wasn't even screen sharing. God damn it. Yeah. You know why you get extra credit? Because your work will be good. You won't waste time in class, pair programming, reading for the first time. Think about how frequently I walk around, it's been 30 minutes and you've written no code. Whose fault is that? Because I am not legally allowed to force you to do anything. I can't make you spend any time outside of class. But how many units are in this class? 4, which means that you are supposed to spend how much time in this class? A minimum of 12 hours. How many do we have in person? About a little less. It's actually about 5.5. So you're supposed to spend 6.5 hours at home or whatever in the lab or something, or come to the office hours. Okay. That's the responsibility, right? Otherwise, if you only put in half of the effort, you get out of it half the result. Okay. So I'll repeat my question. Anyone want to present? Everyone's like, fuck no. All right. Let's just move this around then. Who finished this problem? 9.1. Yeah. Monday. Yeah. I think everyone finished it? Okay, let's do it faster. We did this one, right? Everyone got it. They loved it. And they're like, wow, we're so good. Okay. Did you? Okay. So let's talk about how to do it faster. Okay. So there's two things to do here. One is called over relaxation, what we're about to do on spring break. Right. And the second is the Gauss-Seidel method. And all we're doing here is we're solving the same exact problem. But what we didn't do on Monday is we didn't take into account, say, computationally realistic array sizes. So you had some array, maybe 100 by 100, right? How many dots are in an array with 100 by 100? How many individual elements? 10,000, right? Now, if you double that, how much bigger does the array get? Double the 100? Yeah, you double the 100. 40,000. 40 becomes 40,000. Becomes 4 times as large, right? Now, what happens if you have 3 dimensions and they're all 100? Yeah, that's a lot. And if you double that, right, it's happening as the cube. So essentially what we end up seeing is for 3-dimensional simulations, you start running into computational times becoming important quite quickly. Because almost never are you going to find that you need to simulate something that's 100 by 100. You need to simulate something that's 1,000 by 1,000 or 1,000,000 by 1,000,000, right? You need lots of data points. So how do you work through that in a way that doesn't take 1,000,000 years on your computer? Okay. And one of the ways we do that is over relaxation. Okay. So I want you to go back one step. What does relaxation mean? What does the word relaxation mean? I guess we're not reading after class either. To make use of the relaxation method, you start here, the single place in your phi, it's equal to the average of the things around it. This is how we solve Poisson's equation. By looking at the curvature locally and iteratively updating the values such that they then become smooth. So you start your simulation with something like this. And there's values up here, like this is V, right? And everyone else, it's 0. Okay. So there's a sharp discontinuity. So if I were to just take a single line through here and plot it like a line plot, so this is maybe some distance X, and this is the voltage V, right? In the very first time step, it's a big V, and then it goes all the way down to 0, right? That's a very sharp discontinuity. And what happens in the next second that I update this value of 5? It makes another box. To which direction? Left or right? To the right. It's trying to smooth it out. Part of what we're looking at here is del squared phi, right? What does this operator do? Ever seen this thing before? Del squared? What does it tell us about it? This is an acceleration. This is not an acceleration. This tells us about what? What? Oh, good. That's the right shape. Curvature. Okay. So in fact, what this thing tries to do is it tries to shape phi so that it's smooth. Okay. So this starts up here at V, and the very first thing that it does is it takes a little bit of this and it starts to smooth it out. And then it smooths it out more until the derivative is, right? Because it's got to smoothly go between V over on the left and 0 on the right. Now, smooth does not mean flat. Okay. What we mean is that the way in which it's curving is smooth. Make sense? So if you start with some little bump like this, what happens to the bump? Spreads out. Okay. That's the version of relaxation. So what I try to think of this as, imagine you have some really stiff sheet, right? And you throw it on top of this desk. The first thing it does is it's very flat, very stiff, but let's say it has a little give. So then it starts to slowly turn, and it's going to take on the shape of the thing underneath it. And once it's fully taken on the whole shape, then it'll stop changing. That is the process of relaxation. At every step, we go from flat towards whatever the physics is shaping this object to look like. You started with 2 boxes. They were squares. And what do? They eventually smoothed out until you had 1 over here and 1 over here, and they disappear in between. A nice line in between in which there is no potential, right? So they cancel. Okay. So we are going to do something very similar here. It's called over relaxation. So we're going to do the same process, but we're going to do it faster. We say, well, I don't want to fucking wait that long. So let's just take a bigger step. In between successive approximations, right? I'm going to take, so this is the value at that point, and I'm adding a little bit extra to it. right? The plus equals. So I'm just going to crank it up. 1 plus omega, where omega is a number greater than 0. Right? So if omega is greater than 0, then 1 plus omega is always greater than. But that's definitely true, but then 1, good, right? So it's a number greater than 1. So if I was going to take a step that was, say, 2 squares, and I do 1 plus omega, now instead of taking a step that's 2 squares, I take 2.5 squares. It just gets us there a little bit faster. Okay? That's it. That's the whole code. That's over relaxation. You've now fully understood it, right? Trinity could have had an easy day added to her. It's like, fuck, if I just read. Okay, so let's talk about the Gauss-Seidel method. Okay. This Gauss-Seidel is the Gauss for which Gauss is named, the unit. Okay. Carl Friedrich Gauss. It's not French, but you know what I mean. Okay. So we want to solve Laplace's equation. And the way that we do that is we kind of like walk through the array. Can you see these tiny little dots on the screen? You like walk through every value of the array. So let's imagine like this is the array. Go 1, 2, 3, 4, 5, 6, 7, 8. And then you walk through the whole thing and then you switch them. Right? Right? Gauss-Seidel was like, why wait? Okay. So what we're going to do here is we're just going to update it as we go. So we're still going to start in the top left-hand corner. And as we walk through the array, we're not going to copy it into a new array. We're going to use a combination of the new values and the old values. So let's say you're walking through the array. Oh God, I hate this. Ugh. Let's pretend those are squares. Okay. So you start here, you calculate the derivatives by looking below and by looking to the left and comparing to the boundaries, right? Good. And then you go 1, 2, 3, 4, 5. You go down to here now, and you calculate the derivative below as normal, the boundary as normal, the right as normal. But instead of thinking about the last one, you use the updated value when you're going up. Right? So now you have better agreement as you walk through. And as you get to this one over here, okay, and you're working on this one, you just finished that, you get to here. Now, this one is updated and this one is updated. And you're only comparing to this one that's not updated and the boundary. You see? So that helps the solution kind of converge faster. So what it's doing is the solution is propagating from the boundaries towards whatever the center or whatever the things are, right? If it's from the outside in, or if you have objects inside, they're propagating away from the objects. So you're just helping the propagation go faster. Is that fair?
Spacing is taking this.
What? No, the omega is just between steps. So the omega is as I walk through the whole thing, okay? So let's go up for a second here. So here, phi prime, what you wrote in your code, is equal to phi plus that stuff. And that stuff was your second derivative with respect to x, or your second derivative with respect to y, whatever, right? And you called that delta phi, right? And that delta phi might include 1/4 something something rho or whatever. All of that garbage. Because this is just plus equals, right? So it's plus equals whatever. So the only thing that you do different for over relaxation is instead of saying plus equals whatever, you just multiply it by 1 plus omega, where omega is a number you decide on. Is that fair?
Can it be non-integer? Would be like-
Yeah. In fact, you'll find that it needs to be. If it's like 4 or 5, you're jumping way too quick, right? If it's 0.0000001, you won't notice a difference. So what you'll get to do is a little exploration. You're going to break your code a bunch today. Today is going to be really frustrating, but not because you don't understand it, but because you're trying to tame rocks. You're trying to make rocks use electricity to simulate electricity, right? And sometimes it'll do really poorly, but we will understand it better because of that. Is that fair? So this kind of looks a little bit like we're simulating with respect to time, right? And you might feel when you're looking at it that this is some form of an acceleration or something else. Resist that interpretation. Resist that urge. These are iterations. You have a version of the answer. And you need to compare the new answer to the old answer, right? New answer to the old answer in order to figure out whether or not it solves the conditions, which is basically the little Clausian equation here, right? Is it smooth enough for whatever sources or sinks I have? Okie doke? You stoked? Okay, let's do some warnings. Here's the Gauss-Seidel method. When you do this, you can do the combination of the Gauss-Seidel method with the overall. Okay, sorry, that didn't work. You can use a combination of the Gauss-Seidel method, which is updating with partners that have already been updated, and the over-relaxation, which is the inclusion of omega. And please note that when omega equals 0, you get back normal relaxation, right? So that should be perfectly fine. And so you can create whatever version you want here. Do not write, and you're going to do this because I know everyone does this. Do not write this down. This is not the answer to relaxation. Okay. This is just saying for some values of X and Y, consider the neighbors, but you still need the form of the equation, right? So this one, X plus A, really means I plus 1, right? It's not multiplied by X plus A, nothing like that. Okay. Questions, comments, concerns? Okay, well, that wasn't even a half hour. Could have gotten away with 15 minutes. So that'll teach her to read, right? Someone could have gotten a free pass here. So let's do this. Let's use exercise 9.2. I think that's what it says for us to do today. Is that correct? And we're going to just do example 9.1, square box, voltage along the top, 0 along the other three. Let's use 100 grid points. Okay. And you're just going to take that earlier solution and you're going to introduce over relaxation. And then after you're done with over relaxation, you're going to add in Gauss-Seidel. You can separate them. You can do Gauss-Seidel first, you can do over relaxation first. I don't care. Okay. One thing that you will note is you are going to have a problem. And the problem is that when you wrote your original code, you said something like delta, while delta is greater than the target accuracy. And delta was constructed by taking the old simulation and the new simulation and comparing them. So if you just blindly delete phi prime and say, we don't need this anymore, everything's happening in phi. Guess what happens to delta? It's up to me. Simulation never finishes. It takes forever. Your computer fails. Okay? So hold on to it. Right? It's annoying, but it's fine. Everyone happy? Okay. Break. Yeah, well, I mean, it should probably, right? I'll show you how to make that change. If you sit down and you really struggle with it and you can't do it, let me know. And I can show you what I'm talking about. We can like put it out on the board. We can game plan it together. But spend a few minutes just like drawing your little boxes, your little workflows, and show the flow chart of what is supposed to happen. Okay, so please find your partner for Monday. And we're gonna get cranking on some relaxing. Yeah. Anyone else not here on Monday? Bingo. Thank you.